Previously, we've seen how to approximate a function with a linear equation. So we started off with a function f of x and approximated it with our linearization L of x equal to f prime of a, x minus a plus f of a. Suppose now that we want to approximate our function with a quadratic equation. So suppose we want to approximate f of x with a quadratic. Now this quadratic we'll call p of x, and we'll set it equal to a plus b x minus a squared to the first power plus c x minus a squared. Now we need to find values for a, b, and c, and we're going to do that by imposing three conditions on this polynomial p of x. First of all, this polynomial evaluated at a should be equal to our function evaluated at a. This polynomial's derivative at a should be equal to the derivative of my function at a, and the second derivative of my polynomial should be equal to the second derivative of my function evaluated at a. We're starting off with p of x equal to a plus b x minus a plus c x minus a squared. The first derivative of p of x would be equal to b plus 2 c x minus a, and the second derivative would be equal to simply 2c. If we evaluate these functions at a, p of a would be equal to simply a, p prime at a would be equal to simply b, and p double prime at a would be equal to 2c. Taking these three values and placing them in the appropriate slots in our requirements would tell us that a would be equal to f of a, b would be equal to f prime at a, and c would be equal to f double prime at a divided by 2. So our polynomial p of x would be can be written as f of a plus f prime of a times x minus a plus 1/2 f double prime at a times x minus a. This is known as the second degree Taylor approximation or Taylor polynomial of f of x centered at x equal to a.